Okay, so for section 7.3, we're going to look at computing the value of trigonometric functions of acute angles, okay? And I want to remind you of something that we talked about in the last section. So we had this idea of complementary angles. So complementary angles are any two angles whose sum is 90 degrees, okay? We also know that if we're dealing with a right triangle, one of the three angles is automatically 90 degrees, okay? Now, we know the three angles of a triangle have to have a sum of 180 degrees. So we know that we have to have a total of 180 degrees. We've already used 90 of them. So that leaves 90 left for the remaining angles. So if we call these angles A and B, then angles A and B have to be complementary angles because there's 90 degrees left between the two, okay? And when it comes to this right triangle trig, the stuff that we're doing in this course, there are two right angles that are so common and so frequently used that we really need to study those. The first is the 45, 45, 90 triangle. So that represents the three angles. So 45 degrees, 90 degrees. The second is what's called a 30, 60, 90 triangle. So we need to really study those two triangles and understand how the angles relate to those six trigonometric functions. Okay? Now, for topic one, this video, we're going to look very specifically at the 45, 45, 90 triangle. And what you need to know about this triangle is it is an isosceles triangle, okay? An isosceles triangle has two congruent angles and two sides of equal length, okay? So we need to understand that. So it has to have two congruent angles. Those are going to be the 45, 45 angles. And then the two sides, there's three sides, but the two sides that make up the right angle, the legs of the triangle, those two sides also have the same length. Okay, so let's kind of break that down and see what that means for us. Okay, so example one says in the triangle below, find the measure of the missing angle and the length of the two missing sides. So we're getting ready to build a 45, 45, 90 triangle. Okay, whoops. There we go. My mouse got stuck on something. Okay, so for this one, it says we have the triangle kind of drawn for us. It says, what is the missing angle? Okay, well, we need to know what this angle is here. So we already know this little guy in the corner, that's 90 degrees. Okay, we know that the three angles of a triangle have to have a sum of 180 degrees. Well, if we take 180 degrees and subtract the sum of the two angles we're given, we get 90 plus 45. So that tells me I have 180 minus 135. So that tells me my leftover angle has to be 45 degrees. You could do it like that, or you could say, okay, I know that 90 of my 180 degrees have already been used. That means I have 90 left for the remaining two angles. You could also just do 90 minus 45, which leaves you 45 degrees. Either way, the two angles that are not the right triangle or the right angle have to be 45 degrees each. Okay? Now, the next part of this question says, what is the missing, or what is the measure of the two missing sides of the triangle? Okay, so let's really think about this and let's go back to the definition of an isosceles triangle. An isosceles triangle has two congruent angles. We found those. Those are the two angles that measure 45 degrees. They also have two sides of equal length. So the two sides that make up the right angle, called the legs, have to have the same measure. Well, we're saying in this case that side A is 1. That tells me side B has to also be 1. So side B has a length of 1 because it has to be equivalent to side A. Has same measure as side A. Now, for this leftover side, let's call it C. Okay, we're just going to call it C like we do the hypotenuse. What could we do to calculate the length of side C? Well, we can use the Pythagorean theorem. We know we have a right triangle here, so you can use the Pythagorean theorem to find a missing length of any side of a right triangle. So the Pythagorean theorem says C squared equals A squared plus B squared. Well, A is 1, so we get 1 squared plus B, which is also 1, so 1 squared. Well, 1 squared is 1. 1 squared again is 1. So we have that c squared equals 2. And if we take the square root of both sides, that tells me c is the square root of 2. Okay? And we know that if we have a right triangle and we know the angles of that right triangle and we know the sides of that right triangle, we can then find the ratio of the sides for each of those 6 trigonometric functions. So that's what we're going to do in the next example. So kind of keep this in mind. And let me see if I can shrink it so we can see both at the same time. Yeah, that'll work. Okay, so for example 2, it says using the triangle in example 1, find the exact value of the 6 trigonometric functions. Okay, so we need to remember a couple of things. We need to remember that we have reciprocal identities. We also need to remember the ratios of the 3 like main trig functions, which are sine, cosine, and tangent. So to remember those ratios, we could just use SOHCAHTOA. So SOHCAHTOA tells us how to relate the sides of a right triangle when you're looking at sine, cosine, and tangent, okay? So sine is opposite over hypotenuse. So if we look at a 45-degree angle, let's say we look down here, okay, let me color it in blue so you know what I'm talking about. So if we look at this 45-degree angle, the side opposite that has a length of 1, and the hypotenuse has a length of square root 2. So we get opposite over hypotenuse, which is 1 over the square root of 2. Well, I told you in the previous worksheet, you have to know how to rationalize a denominator. We're going to do quite a bit of it in this course. So to rationalize this denominator, we need to multiply the numerator and the denominator by the square root of 2. Well, 1 times the square root of 2 is just the square root of 2. And then if you take a square root and you multiply it by exactly itself, you just get the radicand. So the square root of 2 times the square root of 2 is 2. So if we're looking at sine of 45 degrees, we're always going to get a ratio of square root of 2 over 2. Okay? Now for cosine, we're still looking at this blue 45-degree angle. Well, the side adjacent to that 45-degree angle, that's adjacent over hypotenuse, would be 1. So remember, cosine is adjacent over hypotenuse using SOHCAHTOA. Well, the adjacent side is 1. The hypotenuse we already know is square root 2. So we have 1 over square root 2. We need to rationalize this. So multiply top and bottom by square root 2. That gives me, again, square root 2 over 2. So on a 45-degree angle, sine and cosine are actually the same. Now, tangent, we know, is going to relate the opposite side to the adjacent side. So SOHCAHTOA tells me opposite over adjacent. Well, if we're looking at that blue 45-degree angle, the opposite side is 1. The adjacent side is also 1. So we just get 1. And there's another way. We also have these quotient identities, and we know that tangent is really the ratio of sine divided by cosine. Well, since sine and cosine are exactly the same, they're square root 2 over 2, when we take square root 2 over 2 and divide it by square root 2 over 2, we also get 1. So you have 2 different ways to prove to yourself that tangent is really just equal to 1. Okay? Now, when it comes to the other 3 of the 6 trigonometric functions, we can use this reciprocal identity comparison or this reciprocal relationship between sine and cosecant, cosine and secant, and then tangent and cotangent, okay? So I know that cosecant is really 1 over sine, which tells me it's really just the reciprocal of sine. So that tells me instead of opposite over hypotenuse, it's hypotenuse over opposite. In this case, we already know that sine is 1 over square root 2 before we rationalize. So before we rationalize, we have 1 over square root 2. Let's find the reciprocal of that. That would just be hypotenuse over opposite, which is square root 2 over 1. And square root 2 over 1 simplifies to just plain old square root 2. Okay? Now, for secant, we know that it has a reciprocal relationship with cosine. So secant is 1 over cosine. We know that cosine is adjacent over hypotenuse, so that tells me that secant is hypotenuse over adjacent. So we get square root 2 over 1. We're looking at this right here. We're taking the reciprocal of 1 over square root 2. And that just becomes the square root of 2. Okay? And then cotangent, we have to remember that cotangent is the reciprocal of tangent. So since tangent is opposite over adjacent, that tells me that cotangent is adjacent over opposite. Well, if we're looking at that blue 45-degree angle, the adjacent side is 1, the opposite side is also 1, so we get 1. Now, there's another way that we can find cotangent. We have the quotient identities, which tells me that cotangent is the same as the ratio of cosine divided by sine. Well, cosine is square root 2 over 2. Sine is square root 2 over 2. When I divide those, either way you slice it, I get 1. Okay, so that is the 45, 45, 90 triangle. This is really important stuff. I'll tell you this, the more you can memorize from stuff like this, the better off you're going to be. Now, we're going to eventually build something called a unit circle, which is going to take all of this, the 45, 45, 90, the 30, 60, 90 that we're going to look at in a minute, and it's going to put it all in this diagram that kind of makes this easier to remember. But I will say, the more you commit to memory, the easier this is going to be for you. Okay, so work on understanding this 45, 45, 90 triangle. In the next video, we'll look at the 30, 60, 90.